Hey guys, so I'll be going over section 12.2 of option D, astrophysics, and the section is stellar characteristics. I won't be going over the whole thing. It'll just be from page 422 to page 427 of the Pearson IB Physics Standard Level textbook. So the first topic I'm going over is stellar spectra. So it's important to know that stars are almost perfect radiators. So this means that, let me write this down, almost perfect radiators. So what this means is that if we have a look here at our spectral diagram for a black body, this means that stars will behave almost exactly like a black body. So all of these curves that are present here, this one, they will apply for a star also, just like they apply for a black body. Now, if from unit 8, which is thermal concepts, energy transfer and stuff, we know that we have been accustomed to this, and we've been accustomed to black body radiation, basically. So we know that as we increase the temperature is given right here. As we increase the temperature, as you see that the temperature is going up, it's the highest here, we know that the graph kinda shifts towards the left. So the average wavelength is right here. The wavelength is right here. So the average wavelength is also going towards the left. So it's decreasing as the temperature increases. But we also know that as the temperature increases, So as we see the temperature increase, we see that this area is getting bigger. This is the biggest area because it's the biggest temperature. So the area tells us about the total amount of power, or the total radiation that is being emitted by the black body, and in this case by the star, since stars are almost perfect radiators. So basically we know that for radiation, for black body radiation, the relationship between power per unit area and temperature in Kelvin is given by the Stefan-Boltzmann law, which is present in chapter 8, unit 8, same thing. And that basically tells us that power, let's go back actually, go back to black. Okay, so power is equal to the area times the Stefan-Boltzmann constant times the temperature, absolute temperature in Kelvin, to the 4th power. Now, since we're dealing with stars here, the power represents luminosity, or how bright it is. So we substitute for P, we substitute L, but it's the same thing. The units remain the same, everything remains the same, essentially. Now this equation is in your data booklet, and the value of the Stefan-Boltzmann constant right here is also in the data booklet, but I'll just write it down. It's 5.6 times 10 to the negative 8. The units are watts per meter squared, per Kelvin to the 4th. So therefore it's negative. Another equation, or another law which is helpful here, is the relationship between the peak wavelength, as we discussed. The peak wavelength. So the peak, for example, for the red one, the red one, is right here. So the peak wavelength would be here, roughly. Similarly, for the blue one, it's right here. The peak wavelength would be here, for example. So the peak wavelength, and the temperature in Kelvin, and their relationship is given by the Wien displacement law, which is also in chapter 8. So feel free to go back and review that. So the peak wavelength is denoted by lambda, or the lambda max, is given by 2.9 to the 10 times 10 to the negative third over temperature in Kelvin. So these, I'm sorry, that's 4. So these two equations will prove very useful. Will prove very useful in what we do, essentially. And there will be a lot of questions asked for astrophysics on these two equations. So make sure you know how to use these. And we will go over some questions, so don't worry about that. So essentially, what the spectra does for us is basically that it helps us, like, we can tell the temperature if we know, for example, the shape of the curve. The shape of the curve is the same as a black body, right? So if we calculate if we get different wavelengths, for example, from the star, different wavelengths of radiation, and we see the intensity of light, which is the luminosity, at those wavelengths, then we can tell what the temperature is, because we know what the shape looks like. The shape looks somewhat like this. It's a pretty rough sketch, but that's essentially what it looks like. And yeah, so basically, if we know a few different points, for example, this one, and this one, 3 in fact, then we can tell that it will be like this, and the temperature is 5,500 Kelvin. So that's very helpful, and that's a concept which helps a lot. Okay, so let's move on to the next topic, which is absorption lines. This has a bit of chemistry in it, so just follow along, try to bear with me. Absorption lines. So what this says is, as the radiation escapes from a star and goes to the outer layer of the star, there are gases present in these outer layers, and what happens to these gases is that they absorb the radiation. So gases absorb radiation. And what this does is that the electrons inside the gases get excited. Just like we're excited for this IB physics test. Not really. But they get excited to higher energy levels. And as they get excited, we see the formation of absorption lines of different colors. So these lines essentially are different for different elements. Different color. So different color for a different element. sorry for the abbreviation here, I could follow along. So this can tell us what is present inside the star, as in what element is there. So most stars have a similar composition. It's just a little bit of fact. So the composition, I'll write it out. Composition, general composition, let's say. General composition of stars is similar. 72% hydrogen, 25% helium, and 3% of other elements. Okay, this is just a side note. Okay. So the darkness of the absorption lines is a good indicator of the temperature of the star, essentially. So high temperature, of course, means a lot of energy, right? So we know that if, for example, if a star is hot, what we will see is that, let's draw the energy levels here. These are the energy levels. So this is the lowest energy level for electrons, and these are the higher ones. Let me draw this energy. So electrons are present basically like this. So for a hot star, the atoms will be ionized, and they will already be excited beyond. This is a hot star. They will be excited beyond, and they won't be present in these energy levels. So as a result, we won't see much absorption. Essentially. So that basically would result in, let's see, that would result in the fact that we wouldn't see visible absorption lines, since nothing is being absorbed. If you look at a colder star, like colder one, not a cold one, but a colder one. So here, these are where the electrons are, mostly. Yes, so we can see that if these electrons gain energy, they will go from here to here, to this one. And that's not a very large energy gain. So since it's a low energy gain, we would see a redder spectral line, essentially. And if we see a redder spectral line, then we know that the star is colder, but not very cold. Like, it's not cold, but it's definitely colder. Now if we move on to, say, a cold star, then we'll see most of the electrons right here. And these, for example, have the potential to get excited all the way from here to here, which is a very large energy gain. It's a large energy gain. Large delta E. So we'll see a lot of energy gain, and the absorption line will appear bluer. It will be on the bluer side because it's a lot of energy gain. So That's how we can tell the temperature from absorption lines, essentially. Okay, let's move on to the next topic, which is spectral classification. Now, spectral classification is helpful to know, very helpful to know in interpreting further graphs and stuff, but it's not asked on the test. So if you want to review stuff, like just for review purposes, then it might be helpful to just skip over to the next section, to just like move the video along to the next section. But if you're seeing this for the first time, then it would be helpful for you to know. So this is easier. There are a few ways to classify stars. Let's see, classification of stars, basically. So the first way is to classify it by temperature. So what essentially happens is they're divided into classes of temperature. So I'll put the temperature here so you can see how they're divided. And since they have a certain temperature, they'll also change color. Okay, so the first class is O. The temperature is very hot. The surface temperature is what I mean. It's 30,000, sorry, this is in Kelvin, degrees Kelvin to 60,000 degrees Kelvin. It's incredibly hot, 10 to 12 times hotter than the sun. It's that hot. The color is blue. So next is B. I'll just write them down and you can see. $7,500 to 10,000. So this will appear white. Then after A, we get F. Let's write this out. G, then K, then M. Okay. This goes from 6,000 to 7,500. This goes from 5,000 to 6,000. This is 3,500 to 5,000. This is 2,000 to 3,500. So this will appear yellow, white. This is yellow, orange, and red. So now there's a second way to classify stars, which is by luminosity, or how bright it is, which is also called Yerkes classification. Luminosity, which is the Yerkes, or the Yerkes, I'm not sure how to pronounce it, but I just call it Yerkes classification, essentially. And as the luminosity decreases, let's see, there are different classes, 1, 2, 3, 4, down for more space, 5, and 6. And based on the luminosity, we also see star size. So essentially we see that if a star is very luminous, it's also very big. That's a correlation that we see. Sorry, there's a 7 also. So this will be, luminosity 1 will be, for example, supergiant. It's a really large star. Luminosity 2 will be a bright giant. It will be bright, and it's not quite a supergiant, but it's a giant. And this is a regular giant. So 4 will be a subgiant, almost giant. Number 5 is a main sequence. Now most stars are main sequence stars, including our sun. And you can see that it's not very bright on the brightness scale. Essentially, it's not very luminous. Then we have a subdwarf. And then we have a white dwarf. Now again, this helps, but you don't need to know this for the test, essentially. Okay, now we move on to one of our last topics, which is the Hertzsprung-Russell diagrams, which we can see right here, which are called HR diagrams. So it looks very complicated, right? But let's zoom in on this a little bit. It looks very complicated, but it actually isn't. Just look at this axis and this axis. So it's essentially plotting the stars. So different stars are in this diagram, and their position is determined by their luminosity, which is right here, and the temperature, which is right here. Now luminosity, you can see it's logarithmic, so it's powers of 10, and temperature about similar, like in a sense, you can say. So if we know the position of a star on this diagram, we can tell a lot of things about it. For example, these stars right here, if we go down, they're not very hot. See, it's when, so the temperature is decreasing as we go to the right. Decreasing temp. And the luminosity is increasing. Luminosity. Okay. Luminosity is increasing actually. So as we look at these red giants, we know that they are cold. Here, they're very cold, but their luminosity is extremely high. If we go here, right here, it's very high luminosity. On the other hand, if you look at, for example, red dwarfs, here, they're also cold, and their luminosity is also very low. If you look at, let's take one more example, white dwarfs, they're on the hotter side, but their luminosity is low. And these blue giants, their temperature is extremely hot, and their luminosity is high. So yeah. Now you can also notice that most stars are on this band, the main sequence band. That's what it's called. Most stars are main sequence stars. Our sun is right here, and yeah, these stars are basically they have a very wide range. They're hot and blue, and they're also cold or red, essentially. So yeah, most stars are in this range, and the specialty about these stars is that they have a core which is undergoing fusion from hydrogen to helium, and it radiates energy through that, creates energy through that, and that energy causes a pressure, and since the force of gravity in the star is so great, that pressure helps it to not collapse, basically. So that's a main sequence star, sorry. Then we see that towards the top right we have red giants right here. So it's they are cold stars. Again, we see the temperature right here. They're very cold stars, but they give out a lot of energy. So they're big. Essentially, they expand more. Their luminosity is about 100 times the size of. Luminosity is about 100 times more than the sun, essentially. And if they're the same temperature as the sun, then that also means that they have an area which is 100 times bigger, or a radius which is 10 times bigger, essentially, at least. So if the temperature is even lower, then we get to this particular class, which is supergiants, which is not mentioned here. They're just giants on steroids, essentially. They're very big and very cold, essentially. They're many times bigger than the sun, like just a radius of 1,000 times of the sun, and the sun is huge, so we know how big these stars are. A common example is Betelgeuse. This star will show up a lot. Betelgeuse, it's a very funny name. So yeah, then we also have white dwarfs. Alright, let's get rid of this. You can go back to see the text that I put here. This should remain. So when we get to white dwarfs, which are right here, we see that they're small hot stars, and they're mostly hotter than the sun, but they're really small, really small, like the size of the Earth. That small, basically. So those are white dwarfs. And you might also have seen this weird thing called the instability strip. Now, this instability strip contains certain stars. There are certain stars here, not all the stars. So not all the stars present here are a part of the instability strip, but there are certain stars here, which are not all of them are here. These stars are called variable stars, and their luminosity keeps changing because of different Cepheid variables or different things. So these are weird, essentially. So we can't really put them down. Another feature of the graph is probably the diagonal lines. You may have noticed, like these diagonal lines. I'll get rid of them so you can see. They also have a number here attached to it. So this number corresponds to the line. So the R is basically talking about the radius of the sun. It's talking about the size. So along this line or above, the radius of the star is 1,000 times or greater than that of the sun, basically. That's what it tells us. For example, or here, if it's here or below, we know that it's 0.01 times the radius of the sun or lower. So that's that. And that basically covers all the content, so let's quickly move on to the questions. So let's go to the questions. So question 11 on page 423. It tells us that Betelgeuse, talking about Betelgeuse, so that comes up again. It's a weird spelling, so make sure you don't get it wrong. It has a radius of 3.1 times 10 to the 11 meters. It's pretty big, ridiculously big. And surface temperature of 2800 Kelvin, basically. So we're asked to find its luminosity. Now remember, I mentioned that this particular equation will help us out a lot. Let's see it. Now we don't have the area, but we know that the area of a sphere, which a star is essentially a sphere, is 4 pi r squared. So the luminosity will basically be 4 pi times 3.1 times 10 to the 11 squared times the Stefan-Boltzmann constant, which is 5.6 times 10 to the negative 8 times temperature in Kelvin to the 4th power, which will give us a luminosity. Again, very high luminosity. The luminosity will be equal to, the luminosity is measured in watts, about 4.2, with some calculator magic we can find out, times 10, let me see what my calculator says here, 10 to the 30th watts. That's our final answer. That's a very big answer. I don't know about you guys, but that looks very big to me. Let's move on to the next question. So on the same page, question number 12. The intensity peak in a star spectrum occurs at 40 nanometers, basically. So this is the value of lambda max, if you remember. We talked about this a while earlier. So we're asked to find the surface temperature and, let's see, power radiated. Power per meter squared, essentially. So for surface temperature, we have a very nice equation here. But first we have to convert this to standard units. So lambda max is 400 times 10 to the 9th meters, basically. And, sorry, negative 9th, not 9th. So for surface temperature, we have this wonderful little Wien displacement law here, which tells us 2.9 times 10 to the negative 3rd over t. So we can, if we just flip it, we can, let me not do that here, some space on the side. So I can find t equals 2.9 times 10 to the negative 3rd over lambda max, which is 400 times 10 to the negative 9th. And that will give me, let's see, about 7.25 times 10 to the 3rd Kelvin. And that's that. Yes. Now for power over meter squared. Power over meter squared is the same thing see as luminosity over area. Now, if we see this right here, basically we're putting area on the other side. So we're dividing both sides by area. So what we'll get is this. And that's easy. We just calculated the temperature right here. So what we'll get is 5.6, which is the constant, Stefan-Boltzmann constant, times 10 to the negative 8 times 7.25 times 10 to the third to the fourth power. And this will give us 1.6 times 10 to the 8. Now be careful here, it's not watts because it's not luminosity, but it's watts over meter squared because it's over area. And that's our answer for that question. Okay. So after that, let's move on to the next question, which is on page 427. So the question's asking us for a particular group of stars, and it's asking us to put them on an HR diagram. So I'll just go to my HR diagram right here, and let's see. Okay, so the first one it asks me for is Beta Pictoris A5V, and let's see. So let me just, it'll be helpful if you can open the book because it'll be hard for me to write all the different ones out. So I'll just put, actually let me write them out. That'll be better in terms of help us to see. 61 AK5, sorry, that's a V. By the way, you won't have these kind of questions on the test. They won't ask you to plot stars on a graph. But this is just to help you understand the graph itself. So if you're reviewing, again, you can feel free to move forward to the other practice questions. Get Beetlejuice again. And that's the last one. Okay, so I'll just put the letter and I'll put the position of the stars. Let me zoom in on this one. Let's see. And that should be it. So that's that for that question, I guess. Sorry about this. Okay, so now let's move on to the questions at the end of the chapter, and I'll go over question 2 with you guys. So question 2 is talking about Barnard star, and it's on page 441. We're moving towards the end of our thing. Zoom in. So we know that the parallax angle is 0.549 arc seconds. Yes. So now there are a bunch of questions on this that will help us. Let's go to the first one. So the first one asks us to explain what a parallax angle is and explain how it's measured with the help of a diagram if possible. So I'll draw a basic diagram and give you a basic explanation. So parallax angle is basically, I'm not going to write everything out, but parallax angle is the angle which is subtended by a star to the Earth when the Earth has moved a distance of 1 astronomical unit, essentially. So, which is just the Earth's orbit radius. That's the parallax angle. So for practical reasons, which means we want the Earth to move as much as it can, so that it so that we can get a more accurate reading to reduce the uncertainty. So we wait 6 months so that the Earth is literally on the other side of the orbit, and then we measure again, basically. And this gives us, and since this is basically the diameter, since Earth is on the other side, which is equal to 2 times the radius, this will give us 2 times the angle. So we have to divide whatever angle we get by half to get the parallax angle, essentially. So let's just say we have this star. It's the same star, but at 2 different times. We have the sun here, we have the Earth in orbit. The sun is centered with this, and we're measuring a distant star right here. So this is the Earth, and this is the Earth here after 6 months, basically. So we look at a closer star first, which is this, and then we look at our distant star. And essentially we look at this angle right here. So this is equal to P, and this is also equal to P. So those are basically our angles. So this whole distance is the distance to the star, essentially. And that's how it's used to calculate, basically. So done. Letter B. Letter B is most straightforward. It asks us to deduce that the distance of Barnard star from the Sun is 5.94 light years. So from the section before stellar characteristics that I was covering, we know that the distance d is equal to 1 over the angle. So we get d is equal to 1 over the angle is 0.549 arc seconds, and we'll get the answer in parsecs, which is 1.82. Sorry. But we need to get it into light years, so we convert it into light years. And this conversion is, I'm I think it's in the formula booklet, but I'm not sure. But it's this. 1 parsec is 3.26 light years. And we get, sure enough, 5.94 light years. That was easy enough. Let's move on. C. So C gives us the ratio of the apparent brightness. So brightness of the Barnard star over brightness of the sun is 2.6 times 10 to the negative 14th. That's the ratio. First, we just have to define the term apparent brightness. So let's define the term apparent brightness. Apparent brightness is a radiant power received per unit area. It's luminosity per area. Radiant power per area received at the earth. So that part is important. Power per area, unit area. Received at earth. That's it. Now, second one, the question asks us, determine the value of the, so we have to find the ratio of luminosity of Barnard star over luminosity of the sun. So let's see what we know here. We know that brightness, let's have this here. Brightness is equal to luminosity over 4 pi over area. So 4 pi distance squared. So this leads us to this. Brightness. Barnard star over brightness of the sun. And this will become a little complicated. And you will see why in a second. So we will have the first brightness equation over the second brightness equation. And this refers to the radius of the Barnard star, and this refers to the radius of the sun, essentially. So we want to clean this up a little. We don't like it this way. It's confusing. So we use our simple keep change flip, and we get to here. Keep times 4 pi s squared over ls. Now the 4 pi's will cancel out, and essentially we're looking for this ratio, this very ratio. So we just move this and this to the other side, and we'll more or less get our answer. So with algebra we get, I'm just going to write this on this side. Times over. Now this value here, we can just put a parentheses here and put both of them squared. So that's fine. Now this value here, we know this value, we were given this value, which was, let's see, 2.6 times 10 to the negative 14. And the value next to it here. Now this is a little interesting, if you see, and in a second I'll tell you why. It's interesting because dB refers to the distance to Barnard star, and ds refers to the distance to the sun. The bottom is obviously 1 astronomical unit, but here we calculated this part. dB we calculated to be 5.94 light years. So we have to convert that into astronomical units. So the bottom ds will just be 1 because it's 1 astronomical unit. Distance to the sun is 1 astronomical unit, and the top will be equal to 5.94 light years, and we know the conversion to astronomical unit is 6.3 times 10 to the 4th, and we squared that value. And our final answer for the ratio, we get 3.6 times 10 to the negative 3rd with some calculator magic. With that, we move on to the final question, which is basically, we know that the surface temperature of Barnard star is 3500 Kelvin. So first, we have to mention why it cannot be a white dwarf. Well, it cannot be a white dwarf. Why is it not white dwarf? Well, if we go back to our diagram, here, we see that white dwarfs are hot. Look at this range. And our star is somewhere over here. It's not hot enough to be a white dwarf, right? So we go back. Let's find it. So the answer is not hot enough. And for the second one, it asks us why is it not a red giant? And for the temperature, we certainly know that it's not. It's hot. It's definitely as hot as a red giant, but we just calculated the. We just found the luminosity, right, with respect to the sun, which is around here, power of 10 to the negative 3rd, and that's important because it will help us, and you'll see why. So the luminosity here, 10 to the negative 3rd, is somewhere here. You see? And red giants are all the way up here. So it's not luminous enough to be a red giant. In fact, if you check here, that's where the temperature is, and that's where the luminosity is. It's a red dwarf, in fact. So let's go back to our question. Where's our question? There's our question. There it is. Okay. So it's not a red giant because not luminous enough. And that brings us to the close. So thank you guys for watching. I hope it helped you. Good luck for the test.